All right, so real quickly on this pH report, you're just going to, again, follow the directions and upload what it tells you. So you're given this table A with 3 different compounds and pHs at 3 different concentrations. So A, what type of compounds um, are 1, 2, and 3, strong acid, weak acid, strong base, weak base, and tell why HCl doesn't have rows for percent ionization or K. So you see these two compounds have those rows here, but this one doesn't. So what is it about that that makes it different from the others? And it has to do with, whether they're strong acids or strong bases or weak acids and weak bases. And I think you should think about it and figure that out. B, you're going to construct 6 ice tables for this case, acetic acid and the ammonia. So you're going to do your ice tables for them and put in the concentrations and use the pH in order to calculate Ka and percent ionization. So this is similar to what you might find in lecture as far as an ice table goes. It might look something like this for a weak acid. Plus A minus, you got ICE. You have the concentrations here, and these concentrations for all of them are 1 molar, 0.1 molar, and 0.01 molar. So you're going to have to do 3 for HA, which is the weak acid, similar to acetic acid, and then the last one's ammonia, which is a weak base. So you're going to have to set up this reaction in water and show what happens to ammonia when you put it in water, and solve 3 ice tables for this guy. And I just picked the 0.1 molar for that situation, and you can pick whichever one you want, but you're going to need to do 3 for each, 1 for each one of those different concentrations, and you can fill out the ice table like you would normally in a lecture problem. And so you see that this should be familiar to you. Now, I have these X's in my ice table, and what you need to do is say, oh, I know how I can solve for X and therefore solve for the K and for the percent ionization. So once you know what X is, you can figure out what K is, for example. So K equals the concentration of H plus, A minus over HA. But I see that that's just X squared over 0.1 minus X in that case. So I need X, but I get X because the table gives me the pH for each one of these solutions, and I know that the pH equals minus the log of H plus. Hey, that's just minus the log of X. So if they give me the pH, which they do in each one of these cases, I could find X. If I could find X, then I could find K, because K relates to X in this way. Now for percent ionization, they're talking about the percent ionization of that parent compound, whether it's a weak acid or a weak base. They both give ions in each case. So I want to know the percent of that broke up. Well, for each one of these products I get, that's how much HA broke up. So X is an indication of how much H plus I get, but it's also an indication of how much HA broke up. So for the percent ionization, I see that X is the percent of HA, I'm sorry, not the percent, it's the amount of HA that ionized. I just have to put that over the initial amount, which is 0.1 in this case, and times it by 100. So again, finding X through pH will give me the percent ionization NK. Over here, though, even though they give you the pH for ammonia, you see that that's not related to X in the table. What X in the table is related to is pOH. So you can get that from pH. So pOH equals 14 minus pH. And then once you figure out pOH, then you know that pOH equals minus the log of OH minus concentration. And again, that'll give you X, and X will allow you to calculate KB, the equilibrium constant for the weak base, and also it will allow you to calculate the percent of that weak base that ionizes in the same way that we did that up there. So you're going to write out those 6 ice tables. This is going to help you with lecture problems of the type that give you the initial concentration and then one at equilibrium. In this case, they don't give you the concentration of one of the compounds at equilibrium. What they give you is the pH, which you can calculate the pOH, and then you can calculate X, or that one at equilibrium. Once you have that, then you can solve for K. So it's similar to a lecture problem. All right, so we're down through B. C says, what are the average Ka and Kb values? So you can calculate their average because these values in the table should be the same. K shouldn't change when you change the concentration. So you're going to look at those values, and it says find their average and also calculate their percent error. So you just need to look up the Ks for these two situations. You're going to find the Ka for acetic acid and the Kb for ammonia, and then compare them to your averages in those tables. Let's see, what is the trend for percent ionization as a function of concentration for weak electrolytes? So you have to look this up if you don't know what the trend is. And so you look that up and you find out that the percent ionization decreases with increasing concentration. And then it says, does the above trend make sense for your weak base and your weak acid? And so you're going to explain that. And if you did the calculations correctly, it should make sense and you should find that trend. And so that's that part. And you're going to upload all that. Then this last part is dealing with the pH of salts. So you have a salts solution. This salt is made up of potassium chloride, and you see that maybe the cation could act like an acid, maybe the anion could act like a base and increase the concentration of H plus or OH minus, but you see in both cases they're the conjugates of a strong. So there's no equilibrium. In fact, this reaction lies way to the left, so far to the left that these guys, these ions, K plus and Cl minus, are considered spectators. They're way, way too weak to react with water enough to change the pH because they're the conjugates of strongs, and the conjugates of strongs are so weak they're spectators. And so that's what we state. Now for this case, example 2 that's done for you, again, there we have a conjugate of a strong, so it's a spectator, but this conjugate is the conjugate of a weak acid. So it's going to be basic. It's going to react a little bit, come to equilibrium with that weak acid, and in the process generate a little bit of hydroxide, and that is going to be enough to make the pH greater than 7. And so you're going to write out these reactions just like they did. You're going to say, okay, spectator, this is the conjugate of a weak, and therefore the pH should be greater than 7. So you're going to explain it in each one of these cases for the ions, where you consider the cation as an acid, question mark, and the anion as a base, question mark, and then go ahead, write it out, and give your explanations. It says A, the experimentally determined pH is given in red. For each salt, complete table B and show the result of possible reactions of the cation with water and the anion with water. The first two are completed for you. So A is pretty much what we just talked about. B, explain you're rationalizing the experimentally determined pH with the reactions you've provided. That is, for example, 2, the pH should be greater than 7 because K is a spectator, but F minus is the conjugate base of a weak acid, so it should be basic. So essentially, just fill out the table. That's all it's telling you to do, and make sure you have both parts. And both parts, I mean, you have the reactions of the cations and the anions with water, and you have the explanation afterwards for why you think that they're going to be reactive or non-reactive. And if they are reactive, then it should make sense as far as the pHs that they're getting reported. And that's pretty much it. So hopefully you can learn a lot about acid-base equilibrium by doing this exercise, and get a good grade.